So what does this mean, first of all? It says all you have to do is replace, substitute x with b, the upper limit, this is not a limit, but the upper, the top, the cap at the top, if you want, minus the value when x is a. So this is the way we will determine any definite integral. So let's go back to our function. Which one will you try? Will you want to start with? You want to start with this ugly one, the last one? Okay, so let's start with the ugly one. And we chose the interval. We chose the interval 0, 2. So we want to find the area between 0 and 2 from the function x cubed plus 2x squared plus 3x plus 1 dx. Notice that this is a differential, the differential of that function. Okay, so please be careful. Good. So now we have to find the antiderivative. So can anyone tell us what is the antiderivative of x cubed? Which function prime will be x cubed? The fourth over 4 plus. Copy the 2. Which function prime will be x squared? Over, excellent, plus 3. Which function prime will be x? Plus, which function prime will be 1? Put everything in parentheses, vertical bar, from what to what? Careful, lower to higher, from 0 to 2. All I have to do is plug in 2 everywhere, because when I subtract and I plug in 0, what do I get? 0. So in this case, I should write that this is the antiderivative, so this will be f of 2 minus f of 0, but this happened to be 0. So then 2 to the 4th, 16 divided by 4 is 4, plus 8 times 2, 16 thirds, plus 4 divided by 2 is 2, 2 times 3 will be 6, plus 2. Do you prefer this or the limit of the Riemann sum? No, everyone is paying attention. Okay, very good. So this is 10 plus 2, which is 12, plus 16 divided by 3, which is 36, plus 16 divided by 3, which is 52 divided by 3. And we checked our work with the limit of the Riemann sum. But we have to learn where it's coming from and so on and so forth. Okay. So now I would like us to continue determining definite integrals for a while. So on page, and then we still have properties and so on and so forth, but I like to practice this for a few minutes. Okay, on page 395, we're practicing the fundamental theorem of calculus. The part, it doesn't matter which number, the part that teaches us how to determine or evaluate definite integrals. As I said, in some books it's part 1, in some books it's part 2. Who cares? Okay, so let's choose. Allow me to choose first. Okay, I would like to choose, yes, 32. 32 as our first example. 32 on page 395. Okay, the integral from 0 to pi over 4 from secant theta times tangent theta, and of course times d theta, not delta theta. Delta is in the limit of the Riemann sum. D theta is part of f prime of x dx. Okay, the differential. Good. So all I have to do is find the function whose derivative is this. Which function I differentially get secant tangent? tangent prime is secant squared. So if it's a product, yes, indeed, is secant theta from 0 to pi over 4. We couldn't even do this with the limit of the Riemann sum. We don't have any formula for secant. Good, so what do I do now? All I have to do is secant pi over 4 minus secant 0. I know secant 0, you don't even have to think in terms of secant, right? So you have to think in terms of cosine. Cosine pi over 4 minus 1 over cosine 0. You don't have to sit there and think, okay, secant, how do I get this? No, just write 1 over cosine, and plug in. So cosine pi over 4, remember it's the only angle whose sine and cosine are identical. Square root of 2 over 2, but it's easier now not to rationalize it, so it will be the square root of 2, correct. So the square root of 2 minus? Yes, and this is it. This is the area under that graph between 0 and pi over 4. Under secant. Tangent. Okay, very good. Next problem. Oh, yes. 39. So now we know how to determine areas on the graphs of functions. So 39. The integral from 1 over the square root of 3 to the square root of 3 from 8 over 1 plus x squared dx. First of all, like before, this is a constant. I don't care for it. Like with limits, like with the summation notation, it's a constant. It can wait outside patiently. So this is the integral from 1 over the square root of 3 to the square root of 3 from dx over 1 plus x squared, or 1 over 1 plus x squared times dx. But I have to determine the function whose derivative is 1 over 1 plus x squared. Which function, when we differentiate it, we get 1 over 1 plus x squared? Excellent. So now you understand why the antiderivatives do not belong in chapter 4? What did we do with antiderivatives in the entire chapter 4? So 4.9 belongs here. Okay, indeed, awesome. So we have 8. Arc tangent x between 1 over the square root of 3 to the square root of 3. And yes, 8 waits for us, is waiting patiently. Arc tangent the square root of 3 minus arc tangent 1 over the square root of 3. When we apply arc tangent to numbers, we get angles back. So the first one is an angle, and the second one is an angle. And what I tell, forget about this for just 1 second. What I tell my students is this. Please do not waste your time to remember anything else other than, so this is pi over 6, pi over 4, and pi over 3. Do not remember anything else but sine and cosine. And here's how. 1/2, 1/2. The square root of 3 over 2, the square root of 3 over 2, the square root of 2 over 2, the square root of 2 over 2. That's all you need. And you can say, well, how do I determine tangent? Very easy. Very easy. This over this. So when I flip it, there is still a denominator. But this over this, when I flip it 1/2, there is no denominator. So the one without a denominator must be this. And the one with a denominator must be this. Of course, this would be 1, so there is no discussion about the middle angle. So this must be pi over 3. So 8 pi over 3 minus pi over 6. But 60 degrees minus 30 degrees is pi over 6, right? 30 degrees. So 8 times pi over 6. And you simplify, and you get 4 pi over 3. And that's it. Please choose another, because then I would like to look at a property. The first property of the definite integral that we are going to look at. And that's the reason why you cannot choose this one first, right now. So after we pick another problem, then we'll choose this, but don't look at those just yet, because we're not ready. We're going to have to look at the first property of definite integrals, and then we will be able to do these. We will be able to determine this. The integral from 0 to pi from f of x dx from negative 2 to 2 from f of x dx. When a function is given as a piecewise, or is a piecewise. So please choose anything else before these two. Which one? 38, this one? Very good, awesome. $38 it is, on page 395. 38. The integral from 0 to 1, hyperbolic cosine t dt. Function times dt, the differential. The differential of the function. Okay, perfect. So then, which function prime is hyperbolic cosine? Very good. Hyperbolic sine t from 0 to 1. I plug in 1, hyperbolic sine 1 minus hyperbolic sine 0. Okay. So let's see what I come up with. Because we remember the definition of sine, hyperbolic. So hyperbolic sine x is e to the x minus e to negative x divided by 2. When we plug in 1, we get e minus e to negative 1 over 2, and minus e to 0 minus e to 0 divided by 2. But how much is e to 0? 1. How much is 1 minus 1? 0. So this is gone. So what is left is e minus 1 over e, everything divided by 2. So 1/2 is in front, it can wait patiently, and then e squared minus 1 over e. Right? Because we have to find the least common denominator. So this becomes e squared minus 1 over 2e. Any questions? I think we should select one more before we look at our first property that I'd like to present to you of the definite integral. So let's see if anything else catches our eye. We cannot do the absolute value just yet in case there's an absolute value over there. Or maybe not. Okay, so let's choose another. 26 it is. 26, where are you, 26? Right here. Excellent. Good pick. In 26, we have the integral from negative 5 to 5 from e dx. Very good pick. Thank you for that. Okay, e is a constant. Who cares? It will wait patiently. Good. So e, which function prime is, I don't see a function here. What is the function here? What is it? 1. Which function prime is 1? From negative 5 to 5. Great job. So e, and now in parentheses, I plug in the upper limit minus when I plug in the lower limit, but I have to put it in parentheses for everyone to see what's happening here. So how much is 5 minus negative 5? How much is 10 times e? It's just 10e. That's it. So the area under the M graph. And it makes sense. How do I know? I just want to show this because it's a very good example. Perfect example. What does this say? It says, draw the function e. Okay, 2, 1, 2, 3. So this is function e. Y equals e. It's a constant. Then I'm going to say that 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. I extend. So I'm asked to find this area. Oops, oops, oops. I'm asked to find this area. So this is -5, this is 5, and this height is e. It's a rectangle. 10 by e. 10 by e. And that's the area under the graph of the function e between -5 and 5. The base is 10, the height is e, the area of a rectangle is 10 times e. And that's how we determine it using the definite integral. Okay, are we ready for the first property of definite integrals? Okay, here's the first property. Let's say I have this function, f of x. And let's suppose I have an interval, a comma b, and I want to find this area. Can anyone give us the formula for this area under the graph of f of x between a and b? The integral from a to b from, which is the height times the base of each subinterval. What is the base? Say it again. No. What did we say? There is no integral without this piece. It does not exist. Without this piece, without the differential of x, there is no integral. Remember, okay, let's go back. This is very important. When we looked at the limit of the Riemann sum, base times height. So in the inside of the integral, this is dx times f of x, or f of x times dx. All of them have to be the same. It's the sum. So these two are in the definite integral, f of x dx. This is the height, and this is the base of the width of each subinterval. Is that better? Because so then the integral from a to b must be from f of x times, right. Please don't forget that. This is crucial because this is the dx and this is f of x. And this is the dx and this height is f of x. Anywhere you want. Is this clear? Okay. So now here's my question. I have a number here somewhere, c. Can I write this? The area, which is the integral from a to b from f of x dx. And please tell me if I can write this. a2 and very good. From f of x dx from f of x dx. Of course I can. Because I can split this interval between a and b into ac and bc. So I have this integral, and then I have this integral. So it could be that I need to split the integral into two. Or it could be that I cannot determine one integral, and I may have to look at two integrals. And here's our first example. Here it is. Either 43 or 44, you choose. 44 it is. So this is a typical example of this property, that we can split the integrals. Of course, we split the limits. We split derivatives. Why not integrals? Okay. Yes?
You put a to b up there. Like the first. No, here, the first
a to b from f of x dx. So the integral from a to b from f of x dx is the integral from a to c plus the integral from c to b. Is that okay? Perfect, perfect. I make mistakes too, so I can go back and correct if there is anything. So in 144 on page 395, so we are asked to find the integral from negative 2 to 2 from f of x dx, and we are told that f of x is a piecewise defined function 2 between negative 2 and 0, and it's 4 minus x squared between 0 and 2. So we want to find the area under this graph, or the definite integral between negative 2 and 2. Can anyone tell us how to find the integral between negative 2 and 2 for such a function? Yes? Very good. The integral from negative 2 to 0 plus, and we'll come back and fill it in, 0 to 2. Of course, there must be a dx. There is no integral without dx. And now let's identify from what? The integral between negative 2 to 0 from what? 2. From 2. Very good. And from 0 to 2 from? Yes. So here we had no choice. We couldn't determine, because it's not the same function, we could not determine the integral between negative 2 and 2 because the function is it's made of two pieces, one piece between negative 2 and 0 and the other piece from 0 to 2. So we had to split, we had no choice. We had to split the integral into a sum of two integrals. And now, which function prime is 2? 2x from negative 2 to 0 plus. Which function prime is 4? Minus. Which function prime is x squared? Over? Very good, awesome. From 0 to 2. Be very careful. Remember, we always plug in the top number and subtract when we plug in the bottom number. And the same thing, we have two different pieces. We have to use two different steps, right? Yes, please.
So if the smaller number ends up being on top, we have to flip it and make it the entire thing negative.
That's another property of the definite integral. I'm going to get to it in a minute. You don't have to, but there are situations in which we have to. But in this case, there is no need. We're just plugging in numbers, right? So when I plug in 0, I get 0, but minus when I plug in the lower limit and I get negative 4. Plus, when I plug in 2, I get 8 minus 8/3. But there is no need to write minus because when I plug in 0, I get 0. So this will be 4 plus 8, which is 12, minus 8/3. So this is 36 minus 8 over 3. And I think I get, what do I get, 28 over 3? Correct my numbers. So the area under the graph of negative 2 to 2, of the graph of f of x between negative 2 and 2, is this. We had to calculate two definite integrals. We found the antiderivative when we plugged in 0, we got 0. We plug minus when I plug in negative 2 and I get this. Plus when I plug in 2, I get this, but minus when I plug in 0, I get 0, so I did not write it. So the opposite of negative 4 is 4. 4 plus 8 is 12, and 12 minus 8/3 is such and such. Excellent question. No. So let's write it down. Excellent question. Absolute requirement the integral from f of x from a to b from f of x dx equals uppercase f of x from a to b, or if you want, f of b minus f of a, works only for continuous functions on a comma b. The question is, what happens if the function is not continuous? Or what happens if one of the limits, either a or b, is infinity? Well, you have to wait until calc 2. Those are improper integrals. So if the function is either discontinuous, or the upper limit or lower limit, or both, are infinities, we have several types of improper integrals. So you have to wait till calc 2. Some of those can be determined and are convergent. Others are not. Very good question. Thank you. I was going to say it, but you asked me, so I said, why not? That's the proper moment to put it in. Yes. If the function is not continuous, the fundamental theorem of calculus is not applicable. And now, since we have this up there, let me ask you this. What is the integral from 1 over x minus 1 from negative 3 to 4 dx? So because the function is not continuous, FTC, fundamental theorem of calculus, is not applicable. Since 1 over x minus 1 is not continuous on negative 3, 1. Excellent question. We cannot apply the fundamental theorem of calculus. The function is not continuous between negative 3 and 1. Is this and 4? Sorry. You know what I meant. So it's discontinuous at 1. The function is not continuous between negative 3 and 4. Therefore, fundamental theorem of calculus, whichever part you want, it doesn't matter, it can be 1 or 2, it's not important, it's the one that teaches us how to find definite integrals, is not applicable here. Perfect question. Perfect. Can we consider the next property then? Here's our next property. The integral from a to a from f of x dx. What do you think this equals to? Of course, 0. There is no interval. If there is no interval, there is no area. It's like the interval from 1 to 1. There is no width. There is no base of any subinterval. Perfect. Very good. Here's the next property. Even function. Symmetric interval. These two together in one piece. So let's look at an even function. Can anyone give us an even function? The simplest one that you can think of an even function. Of course, that's the simplest we can think of. And also the absolute value, but that's more involving. Very good. So here it is. So this is f of x equals x squared. We are going to use a symmetric, it's an even function. We're going to use a symmetric interval. Let's say between negative a and a. And we want to determine this area. This area will be the integral from negative a to a from f of x dx. Even function, symmetric interval. Both are required. Even function, symmetric interval. Negative 1 to 1, negative 3 to 3, Negative 10 to 10 from a function that is even. Okay. Would you agree that this piece has to be identical with this piece?
Yes.
That's all we have. There is nothing else. This is always easier to determine. An integral or calculate. The integral from 0 to a number is always easier to calculate than the integral from -5 to 5. But remember, two conditions have to be fulfilled. The function must be even, and the interval must be symmetric. Otherwise, you cannot write this. Okay, the second combination is obviously odd function and what? Of course, and symmetric interval. Odd function and symmetric interval. So let's do that. Let's look at a graph. Can anyone give us an odd function? X cubed indeed. I completely agree with that. So this is x cubed. F of x equals x cubed. And we're going to use a negative a and a positive a. And please tell me what is the integral from negative a to a from f of x dx when the function is odd. Of course. Identical pieces, however, one is positive and one is negative. So therefore, two conditions have to be fulfilled: symmetric interval and odd function. I'd like to look at a couple of examples. Let's say the integral from -2 to 2 from x to the fourth plus 2x squared dx. Every time I am asked to look for the evaluate the definite integral, I will always check as the first step, is the function continuous between -2 and 2? Yes, it's continuous. This function is always continuous. Number two, I look at the given interval. Is it a symmetric interval? Yes. Number three, I identify whether the function is odd or even. If you say odd, I'll write 0. If you say even, I'll write twice the integral from 0 to 2 from that function. Is this odd or even or none of the above? If it's none of the above, then I have to continue step by step and determine this. It is even. Would you agree? Because f of -x is the same with f of x function is even. Therefore, I will definitely do this because it's easier to calculate. Do I have to? No. But this is a property of the definite integral of an even function on a symmetric interval. So then I copy the 2, which function prime is x to the fourth, right? And then plus 2, x to the third over 3 from 0 to 2. It is much easier to plug in 2 than to plug in -2. And in this case, since I have 0, I don't even need to plug in 0 because it's all 0. All zeros when I plug in 0. So it's 2, 32 over 5 plus, so that's 8 times 2, 16 over 3. The least common denominator is 15. The first one needs a 3 and the other one needs a 5. So 94, I'm sorry, as I said, today my numbers are way off. Plus, I think this is 80. I'm checking everything now. Yes, it is 80. Good. So then 2 multiplied by, I think this is 176. Please do not hesitate to correct me. So 8 plus 6. So I can simplify by 3. Yay! Okay, if 17 divided by 3 is 5. See, I told you, don't trust my numbers today. No, I can simplify by 3, I wish. So 14, 15, and 1, and 3, and I got this as the final answer. Yes? Am I okay with the numbers? Okay. Here's another example, and I like to copy one from the book. Okay, ready? The integral from negative pi over 3 to pi over 3 from x to the 4th sine x dx. First thing I need to do whenever I'm asked to calculate a definite integral, I will look at the function and see whether it's continuous on the interval negative pi over 3 to pi over 3. Is it? Yes, x to the 4th is continuous everywhere, sine is continuous everywhere. The product of two continuous functions would be always continuous. Perfect. The second thing I observe is that the integral is on a symmetric interval. And now, finally, I ask myself, is the product or the function x to the 4th sine x odd or even? If it is odd, then I'll put 0. If it is even, then I'll write equals 2 times the integral from 0 to pi over 3, blah, blah, blah. Any function that has sine in it cannot ever be even. Ever. Unless it has sine squared. Because sine squared, when you plug in negative 1, you will get negative sine squared, but then you have to square it. But every time you see sine in it somewhere, or any function, any trig function that has sine in it, not secant, not cosine, those two are the only ones that don't have sine in them, right? But tangent, cotangent, cosecant, those functions have sine in them. They will not be even. Again, you have to be careful powers, blah, blah, blah. So x to the 4th is definitely even, but sine to power 1 is definitely odd. That makes the entire function odd. So the answer is 0. And I have to write odd function on a symmetric interval.
Could you manipulate it so that, like, if the interval was different, like, say you add like an extra, like this pi over 4, but you could still, or pi over 2 for the top one.
Okay, so you wanted to, if one of the limits is different, you would like to look at that integral and get 0, and then just look at the rest of the piece. I agree. It is very possible because we know the property that the integral from a to b is the integral from a to c plus the integral from c to b. Yes, you can do that. Yes. Ready for the next property? Okay. We already heard this today from the integral from a to b from f of x dx is the opposite of the integral from b to a from f of x dx. That's another property. We will be using this when we get to talk about the fundamental theorem of calculus, the other part that we don't need to talk about it right this moment. Any questions so far? Any questions? So I just wanted to show you. I don't want to talk about the part 1 because it takes a little bit longer. But let me just show you. This is on page 393. Let me just see where it's at. So this book considers that this is part 2, which says the integral from a to b, from f of x dx is f of b minus f of a, where f is any antiderivative of f. That is, f prime is f. We know that, right? So when we differentiate this, we get that. That's why I always ask, what function prime is that? Right? So that's the antiderivative. And then the fundamental integral calculus shows us 2 things. One, how to calculate the definite integral. And this one says that differentiation and integration are what types of, what is the relationship between them? Differentiation and integration are inverses of each other. So if I have a derivative and I apply the integral, I get the function. If I have the integral and I differentiate it, I get the function. So these are like log and exponential. They are inverses of each other. But we're going to get to that. Any questions? Any questions? Okay. Ready for the next property? Okay. Let's take a look at the following scenario. I have a function. Let's say f of x. I have another function. Let's say g of x. Would you agree if I write that f of x is greater than or equal to g of x on the integral a comma b? I don't know, outside of that anything can happen, but I'm only focusing on the interval a comma b. So if I show that f of x has higher values than g of x on the interval a comma b, here's our next property. Therefore, the integral from a to b from f of x dx must definitely be greater than the integral from f of x from g of x dx. Of course. How come? Here it is. This is the integral under g, or the area under g that is determined, that is calculated with this. And this is the area under f that is calculated with this. Of course this area is bigger than this area. So what we have just learned is that if we have an inequality, let's say, give me a function that is smaller than another function on an interval. That is harder to determine, right? So for example, let's say the square root of x plus 2 and the square root of x plus 9. Which one is definitely larger, let's say between the interval 1 comma 4? Right, so this one is bigger. So would you agree with this? Is the square root of x plus 2 less than or equal to the square root of x plus 9 on the interval 1 comma 4? These are increasing functions. So therefore, the integral from this function dx on the interval 1 comma 4 will definitely be smaller than the integral from 1 to 4 from the other one, because one is above and the other one is below, so the area is bigger for the second one than the first one. Would you agree? Yes? Okay. We need a couple more properties before we look at a problem like this. Or maybe I can simply work on, yes, I can. Because we have examples. Or I can make one up, it's okay. 56. Use the properties of integrals, of definite integrals, of course, to verify the inequality without evaluating the integrals. We don't even know how to evaluate this. We don't have the tools right now to evaluate these two integrals. So they're giving us the relationship So this is page 384, 56. And we are told that the integral from 0 to 1 from the square root of 1 plus x squared dx is the less than or equal to the integral from 0 to 1 from the square root of 1 plus x dx. Okay. They're telling us, show this. Well, I have to build this step by step. I cannot just show or say, oh, it's obvious. No, it's not obvious. And I have to show step by step. My starting point is this, that x is a number between 0 and 1. That's my starting point. That's what I know so far. That x must be a number between 0 and 1. Notice that I am going to look at this with a square root, and I'm going to look at this with a square root. So for now, let's take a look at this piece. Meaning, I'm going to add 1 to all three sides. So I have 1 less than or equal to x plus 1 less than or equal to 2. When I take the square root, and you can say, well, you told us a long time ago, and I'm pretty sure I did, you can take the square root from inequalities. You can from equations, but not from inequalities. In this case, I can, because they're all positive, and I can take the square root from all three. So when I take the square root, I will have 1 less than or equal to the square root of x plus 1 less than or equal to the square root of 2. I just wanted to see for now what is going on with this quantity. So this function for the interval 0 to 1 is a number between these two. Okay, fine for now. I want to come back here. I start again, so this is one piece. I start again with 0, x between 0 and 1. But this time I want to build an x squared. These are positive numbers. So when I square, I still get this. And of course, I'm not ready yet. I have to add 1 to all three sides. So 1 less than or equal to x squared plus 1 less than or equal to 2. And now I'll take the square root to get this. I'm going to write it as is written there, less than or equal to the square root of 2. So this is the other piece. And you can say, well, what have you accomplished? Not much. I can only say that they're both between 1 and the square root of 2. So I still don't know which one is bigger. Well, I do. So finally, I would like us to compare 1 plus x squared to 1 plus x. Because according to this, I haven't made any progress. But always keep in mind that in our example, x is a number between 0 and 1. So which one will be bigger? 1 plus x or 1 plus x squared? I'm only talking about numbers between 0 and 1. Because when you square x, you get a tiny number. If you have numbers between 0 and 1, and you square those numbers, they are smaller than plain numbers between 0 and 1. Would you agree with that? Because 1/2, when you square, is 1/4, right? So for 1/2 in that interval, this is 1/4 plus 1, but this is 1/2 plus 1. So obviously this is a number that is bigger between 0 and 1, not everywhere. But between 0 and 1, 1 plus x is a bigger number than 1 plus x squared. Would you agree with that statement? Okay. Because they are all positive, yes, I can take the square from both sides. I already established that the left function is smaller than the right function. Therefore, the integral from 0 to 1 from f of x dx must be less than or equal to the integral from f of x dx from 0 to 1. By the property that says that if a function is less than another function on an interval, the area under the first one is smaller than the area under the second one. That's all we needed to show. we didn't need to do anything else. So we proved that the integral from the square root of 1 plus x squared is less than or equal to the integral from the square root of 1 plus x on the given interval 0 to 1. Any questions? I know we have 3 more minutes. Let's finish up with one problem. I'm looking at this one. Write as a single integral in the form the integral from a to b from f of x dx. So this is problem 47 on 384. Last one for tonight. (47). We have the integral from negative 2 to 2 from f of x dx. And we have plus the integral from 2 to 5 from f of x dx. And minus the integral from negative 2 to 1 from f of x dx. They want us to write this using one integral symbol. So let's take a look at what we have. Between negative 2 and 2, between 2 and 5, these are all added. So how will you change this? Just the first two. What will you write for the first two? The integral from negative 2 to 5, very good, from f of x dx, minus the integral from negative 2 to 1 from f of x dx. But the integral from negative 2 to 1 is this piece. So from the integral from negative 2 to 5, I want to subtract the integral from negative 2 to 1. So what are we left with?
1 to 5.
Excellent. The integral from 1 to 5 from f of x dx.